Hello class, let's discuss week 13 group homework. My solutions. Number 1, explain what it means to calculate A over B or A-bths of something. Several students just attempted to describe what this means all by itself, by like a fraction A over B. If you look at just the symbol A over B by itself, and then you might argue that it stands for doing some sort of partitive division, A divided into B parts or something. That'd be a good explanation. But when you are thinking about A over B of something, then I'm asking you to really think about what happens if you have A over B and you're multiplying it by some amount. I'll put C there. Like, what do you do to C when you see a mathematical expression that says to multiply C by a scale factor of the fraction A-bths? And so my description here is to partition the something, whatever the something is. You partition it into B equal parts first, and then you iterate one of those part A times. We're going to see that put into work right here on this very next problem. Express the length of the blue strip as a common fraction multiple of the orange strip. All right, so if I were to, when you see these instructions here, the blue strip, we're expressing the blue strip as a common fraction multiple, so some sort of A over B multiple of the orange strip. I'll use a big O for the orange strip. So we're trying to figure out what fraction you would multiply the orange length by in order to get the blue length. And I've partitioned the orange and blue into equal parts. You can see the orange has 4 parts, the blue has 7. But if you start with the orange, so start with something this long, we'll say. Okay, so we'll say we have, move that around, there we go. So we got something that's the orange length. We're going to partition it into 4 equal parts, and then focus on one of those parts right there. And then copy that part, iterate it 7 times to get this length. So in other words, I wanted to do first 1/4 of the orange and then do 7 of those. So as a 2-step process, it would look like this. We do 7 of 1/4 of the orange. And then of course, that just means do 7/4 of the orange. Whereas when you go the opposite direction, when you start with the blue, so I start with the red as it is, I want to find 1/7 of the blue. So partition the blue into 7 equal parts and focus on just one of those parts right there. But then iterate that part now 4 times to get the orange. So if you start with the blue, you do 1/7 of it first to get one of the parts I have drawn above. And then 4 of those parts would ultimately create the same length that's the orange. So in other words, you just have 4/7 of the blue. I was a little bit disturbed that, oops, I have a bunch of stuff accidentally deleted. I'll fix that later. There's a bunch of words all of a sudden missing right there. I was a little bit bothered or upset, or not upset. I was disappointed maybe that I didn't maybe emphasize this enough in my lessons, but very few groups, if any, described this in a way I thought was very clear. And if you can't describe it in a way that's clear to you on paper, you might struggle with how to describe it to a child when you're teaching this. You know, things, what you write on paper should make sense, at least using the words partition and iteration in the way that most people, most mathematicians use them. So that's something I think I want all of you to think about whenever you are trying to do a fraction times something, is to think of it as that 2-step process. Partitioning followed by iterating. Partitioning followed by iterating. Next one, we were given the information that the blue strip was 5 3/4 feet long. That's the same thing as 23/4 feet long. And if you want to scale that to 1 foot, then if you take 23/4 and do 1/23 of it, you're going to get down to 1/4 of a foot. But then you have to do 4 of those to get back up to 1 foot. So again, you have this partitioning followed by iterating to reconstitute 1 foot. And then when you put these this 2-step partition followed by iterating together into one fraction, their scale factor is really this. So this is really just simply saying that if you start with 23/4 feet and you scale it by its reciprocal, 4/23, then you're going to always wind up getting back to 1 unit, in this case 1 foot. So reciprocal scale factors are the way to scale things back to 1. Number 2, how many batches of biscuits could be made? 4 cups. All right, so the key is when you're trying to figure out, this is a multiplicative relationship, and identifying the multiplicand, again, is the easiest way to do this. And you're looking for the number that indicates that it's a unit of something per unit of something else, and that shows up at the 1/3, because it's 1/3 of a cup of sugar is required for each batch. That language right there tells us that this 1/3 is a cup per batch. So that goes right here in the role of the multiplicand. It's 1/3 cup of sugar per batch. And then the multiplier should be units of batch, right? The unit of the multiplier should match the denominator unit of the multiplicand, and then the unit of the product should always match the numerator unit of the multiplicand. And so the only other bit of information here was the 4 cups of sugar, and since that's cups of sugar, that belonged here in the product. So we're trying to say, okay, well, each batch, we're trying to figure out how many batches. We're going to multiply that by 1/3 of a cup per batch and get to 4 cups. If you take the sort of context out of it, you're trying to say, hey, what do I multiply a third by? How many copies of a third does it take to make 4? And that's as simple of a question as we're asking when you strip all the units away. How many copies of 1/3 make 4? This is a quotative division question. And so here's the missing quotient division statement, where we have 4 cups divided by a third cup per batch, and that will give us how many batches we have. So if you just reached for a calculator and did 4 divided by a third, that would be the correct operation for answering this question. This is a case of quotative division because we are looking for a missing multiplier. And then the illustration, and there's lots of ways to illustrate this stuff. I did bars here to illustrate. First I drew a picture of, well, I recognize that this number 1/3 is less than 4. So I tend to draw the larger number first, although, that doesn't really matter. And I drew the 4 cups, and then in a separate picture I drew a 1/3 cup to represent a batch. So here's my representation of a batch, what's shaded anyway. This part right there is a batch. And since we're trying to figure out how many batches we can make, we want to really just figure out how many copies of the blue strip does it take to make the green strip. And since you can just count them out, we don't need to do any partitioning, only iterating is required here, because if I iterate the blue strip 12 times, I will get the entire green strip. So 12 1/3 will make 4. So in other words, 12 batches. And then I didn't ask you guys to do this in the instructions. I wish I had, but I also just used the algorithm to confirm the answers after we set this up. And the algorithm, of course, what I mean by that is when you divide by a fraction, multiply instead by the reciprocal of the fraction, and then multiply those, and you get this 12. But a student has to know that they have to understand this structure to begin with so they can set up the correct division in the first place to get the answer. So even if we're trying to be more efficient, not draw pictures to make sense of this, they still have to understand these ideas here so they know what to type into a calculator. 4 divided by a third. Here's another case. Maurice, I'm looking for the multiplicand. And it looks like that's the question. Look, notice the question, how it's phrased. Determine how far Maurice walked each hour. That phrasing, the each hour, is a per hour phrasing. That means we are looking for the multiplicand in this case. So we are trying to figure out how many miles per hour Maurice can walk. And let's see, he went 14 miles. So the miles goes is the product, because the product and the numerator of the multiplicand should have the same unit. And then the other information was the 3.5, which is the same thing as 7/2 hours. So I put 7/2 hours here. That's the multiplier, whose unit matches the denominator, right? So once I feel pretty confident I've got this structure in place, I recognize it's a partitive division that will answer the question because it's a missing multiplicand. And then we do product divided by multiplier, and we're going to get the missing multiplicand. And that's a partitive division that's happening here. I chose to model this one with almost like it was water in buckets, if you will. I thought of each hour, so I drew representation of the 7/2 hours first. And there are ways to do this where you draw a representation of the 14 miles first, and you try to break that into 7/2 groups. In fact, yeah, I do that as well down below. So I do this 2 different ways here. I start focusing on the 7.5 hours, and I think of each of them as like a group, or like a bucket, if you will, a container. So these boxes here represent my 3.5 hours. But then I recognize that's the same thing as 7 halves, right? So there's 4 halves right there, and then there's 3 halves up here. So there's really just 7 halves sitting here, but 7 equal-sized boxes now. And so if I take the total distance of 14 miles and I divide that by 7, then I can recognize that there's going to be 2 miles in each half of a box here, or in each half of an hour. And then, of course, if you repopulate an entire hour, you could see 4 miles. So each hour, Maurice walks 4 miles each hour. And then in the last half hour, he just walks 2 miles. So he gets 14 miles walked in 3.5 hours. And so the operation you would do on the 14 divided by 7 halves is you would take 14, which 14 miles is in all of the boxes, divide it first by 7, right? So we have 14 miles he walked. First do 1/7 of it. That gives us how much is in one of these. And then iterate that twice to get 1 hour. So notice that we do 2/7 essentially. That's 2 times the 7. So 2/7 of 14 in order to answer 14 divided by 7 halves. Well, that you can see the invert multiply algorithm happening here. And that's that helps understand why the invert multiply algorithm even works in the first place. I do the algorithm down here. I just did 14 divided by 7 halves, inverted, multiplied, etc. I got 4 as an answer. Here in the second attempt that you see right here, I used line bars just to show you varieties of things. And I first drew the 14 miles. And I knew that 14 miles corresponds to 7 halves hours. And so that's 7 1/2 hours. So if I divide 14 by 7, then I'll know how many miles we go every half hour. And that gives me this, this blue or orange part right here. So in a half hour, we will go 2 miles. Because 14 divided by 7 is 2, and 7 halves divided by 7 is a half. So here's the 2 miles, and that corresponds to a half an hour. Notice I'm not drawing any lines that represent hours, although I could. I could draw, a separate bar and say how long is an hour, etc. But I didn't bother doing that. I'm just keeping track of. I'm only focusing on miles right here. But if you go 2 miles every half hour, then you're going to go 4 miles every hour. Right, so you can see then that every group of 4, there's an hour, there's 4 miles, another hour, here's another hour, and of course here's that half hour at the start. But 3.5 hours would take to go 14 miles. There is no one correct way to model these things, but there's lots of valid ways that make sense. And the key really is using labels so students can realize that don't just put 1s and 2s all over the place. It's extremely confusing. Same thing down here. If I just put a 2.5, it's like, what are you talking about? 2 what? 1/2 what? So always putting labels on the numbers you put and recognizing that you're really coordinating 2 different quantities. You're coordinating distance and you're coordinating time. Number 4, we are told that Curtis can run 8.5 miles each hour. That's that's 17 halves miles per hour. That's the multiplicand. We're told how far he can, or we're curious how long it will take. So how many hours will it take to run 11/4 miles? So it's a missing multiplier, quotative division at play. I drew comparing these two fractions here, and we're doing quotative division, so we're really trying to figure out how many 17 halves does it take to make 11/4. But 17 halves is much longer. Here's 17 halves, and here's 11/4, 2 3/4. So we're trying to say how many greens does it take to make red? Well, this is the exact same questions that we have like up here. Like how many blues does it take to make orange, or how many oranges does it take to make blue? The ability to scale to make it larger or to scale to make something smaller is what we were practicing up here, and it's really kind of what you're using down here every time you do quotative division. Here we are. So we're starting with the green. That's our 8.5 miles, and it corresponds to 1 hour. And we want to scale that down to figure out how long the red is in terms of the green. Like, what would you multiply green by to get red? Well, that's whatever you do multiply green by to get red is what you would multiply an hour by to figure out how long it takes to walk the red length. Okay, so I first did 8.5, and then here was 2 3/4. And a good practice when you're comparing these strips, but they have different denominators in their fractions, is to rewrite the strips in such a way that they have the same denominator. So I thought of 17 halves as 34 fourths, and I broke, you'll notice I did fourths right on each of these. And you can count them out, right? There's going to be a total of 34 fourths here. That makes 8.5. And here there was 11 fourths. And so once everything is in terms of fourths, it's very easy to see. Think of each fourth of a mile as a single unit, and there's 34 gaps here, if you will, and here this one is only 11 gaps. So it's pretty easy to see that if I scale 34 down by 1/34, then I'll get the length of just one of these little gaps right here, and then I iterate that 11 times and I reconstitute the red. In other words, if I do 11/34 of the green, I will get the red. So we do 11/34 of an hour, because the green also represented an hour. Scale that down by 11/34, and we have the total time it would take. And then here's the algorithm to confirm that, 11/34 of an hour. And here we have the given information that we knew was that a liquid weighs 5 1/4 pounds per gallon. So that's our multiplicand. So 5 1/4 is 21 quarters. So there's our 21 quarters pounds per gallon. We're looking for how many gallons. So that's the multiplier in this case, because that gallon should match this gallon down here. And then the other information we know is that 5 halves pounds. So this is, again, quotative division. And this one's pretty similar to the last one. Once again, the amount per gallon is more than the amount that we're trying to scale to. So we're starting with a larger amount. Here's my 5 1/4 pounds, or 21 quarters. And we're trying to scale that down to 5 1/2, which I'm going to write as 10 quarters. Right? Get that common denominator is a good approach when you're doing quotative division questions, when they have the same denominator. And so now we can really just see, to turn green into red, I'm going to scale green down by 1/21. That gives me the length of just one of these little pieces, and then iterate 10 copies of that to make the red. So in other words, if I do 10/21 of the green, I will get the red. So 10/21 of a gallon will correspond to 5 halves pounds. And then the algorithm, of course, is done down here and confirms that we get this 10/21 figure. Number 6, 4/5 of a container holds 3 1/3 gallons of water. Determine the capacity of the container. Or the capacity of the container is how many gallons it can hold per container. That is the multiplicand. That's what we're looking for, how many gallons per container. And we know that we have 4/5 containers and we have 10/3 gallons. That corresponds to 4/5 containers. And so we are really doing a partitive division, trying to find a missing multiplicand. And you could think of it as we have 10/3 fits 4/5 of a container, or fills 4/5 of a container. Then we're looking for how much fills an entire container, which is what partitive division answers. It gives us that multiplicand. And here in this case, I did a drawing of something that looks like a container, just because it seemed easy to draw and think about. So here's a whole container, and 4/5 of it right here filled up, and we know that that corresponds to 10/3 gallons. Well, we're going to scale that down by 1/4 to figure out how much we have in just one of these pieces, and then iterate that 5 times to reconstitute the entire container. In other words, those steps are summarized right here. Start with 10/3, which is what's shaded in blue. Do 1/4 of it. That'll give us one of the pieces in blue, and then do 5 of those, and that would reconstitute the entire container. Notice I'm not saying, the question isn't how much water is in the container, because then we would just give this answer again, because this is how much water is actually in the container. We're asking for how much water would fill the container. In other words, if you added more water and filled the container, how much water would there be after that? Or in other words, simply, what's the capacity of the container? That's the good way to ask it when your container isn't actually full. Just say, hey, what's the capacity of it? So we do a 1/4 of 10/3, that's 10/12 or 5/6. That's how many gallons are in this piece, and then you just do 5 of those and reconstitute this. But notice you see the invert multiply algorithm happening. When I'm doing 10/3 divided by 4/5, and we're trying to reconstitute the capacity of a container, then we do 1/4 of 10/3 and then 5 of those. In other words, I do 5/4 of 10/3, which is what happens when you invert 4/5 and just multiply it to 10/3 instead. And here I did a different approach. I did a number line approach. Feel free to look at that. I'm not going to talk about it, but just to show you variety, that you don't always have to, you can do a lot of this work in these problems with these number lines. But actually, I do want to comment on something here. So I first drew 10/3. And at first I didn't have these little hash marks that you see. There's a little hash mark. I didn't have those. I just thought of this in terms of thirds. But then, so 10/3 of gallons, I recognize that that's 4/5 of the container. So I want to first do a fourth of that. But doing a fourth of 10 does not produce a whole number. Right? Doing a fourth of 10 doesn't produce a whole number. So I scaled 10/3 up to 26ths. And by the way, when you do something like, when you do this, I see too many students still doing this. When they're doing the changing, writing an equivalent fraction, they just put a single times 2 when they do that to top and bottom and write to change the fraction. When you put a single times 2 here, that's not, this is extremely confusing to a person who's just reading your work, because this is a false statement. When you double 10/3, you get 20/3. You don't get 26ths. You get 20/3. You only double the top when you double a fraction. You're not really doubling the fraction anyway. You're just trying to rewrite this in an equivalent form. So when you put your times 2, write it top and bottom, please, so that it makes more sense what's happening here. You're not changing the fraction. You're simply rewriting it in a new form. What I mean is you're not changing the value, right? 10/3 is the same size as 26ths. And so this produces an equal sign that joins the original fraction and the new fraction. Those are equal values. When you put a single times 2, when you just write times 2 and then you say 26 next, it's true that this expression is equal to 26, but 10/3 is not equal to 26. When 26, how do I want to say this? 10/3 is the same as 26, but 10/3 times 2 is not the same thing as 10/3, so it's not the same thing. I mean, this is just a false statement when it's written on paper like this. You must write this. If you're trying to just do an equivalent fraction, write your times 2 twice. Your students will thank you for that. Anyway, I scaled up, or I rewrote 10/3 as 26. The reason I did that is because that 20 is easy to divide by 4. So we have now that 26 gallons corresponds to 4/5 containers. So I know I want to do 1/4 of 26. Oops. 1/4 of 26 is easy. That's 5/6. So 5/6 corresponds to 1/5 of a container. And then that's why I did the extra hash marks later, these extra little hash marks, because I wanted to think of everything in terms of sixths. And so we can see we have 1, 2, 3, 4, 5, 6. Right, we have 6, 12, 18 plus 2 more. We have 26 here. Divide that by 4. That makes 5/6. So 5/6 gallons corresponds to 1/5 of a container. And then now I just had to iterate this 5 times to get, so do 5 times this and 5 times this. 5 times a fifth gives you 1 container, and 5 times this gives you 25th, 6th containers, and that's, or sorry, gallons, and that's how much would fill 1 container. Okay, number 7, 1/4 of a ton of gravel is evenly spread over 1 3/4 acres of land. Determine the weight of gravel that covers 1 acre. So this phrasing, determine the weight of gravel that covers 1 acre, is clearly the multiplicand. It's tons per acre. That's what T and A stand for, tons per acre. So the 1/4 ton is on this side, and then the 7/4 acre is on this side. It's the multiplier. So we're saying 7/4 acres times how many tons per acre will give me 1/4 ton. So we're going to do the division. This is a part of the division. We're going to do a 1/4 ton divided by 7/4 acres and figure out how many tons per acre we have. So in my drawing, I drew boxes to represent 1/4 acres. All right, so we have 1 acre right here, 4/4, and then 3/4. So there's 7 parts here. There's 7/4 acres. And that constitutes 1/4 ton. So if I want to figure out how much is in one box, any one box, then I have to do 1/7 of a quarter. So that's what we get right here. So 1/28 of a ton is in each box. But now we want to answer how many are in the entire acre, how many are there per acre. So you have to do 4 of those to get this. So I do 4 copies of 1/28. So I get 4/28 of a ton. That simplifies to just 1/7 of a ton. So we have 1/7 of a ton right here. in 1 acre. And then the invert and multiply algorithm produces the same numerical answer, 1/7. And number 8, the last one, we're doing batches of wonton soup and soy sauce. We are told that 2/3 of a cup of soy sauce is required for each batch. That's a multiplicand right there. That gives us this part, 2/3 cups per batch, C per B. And we're trying to figure out how many batches, so we don't know the multiplier, but we do know the product, 7/3 cups. And so this is a quotative division case where we have 7/3 divided by 2/3, and with the interpretation of how many 2/3 does it take to make 7/3. And that's going to give us how many batches we need. So I drew the 7/3 cups. That's how much we have. That's the longer amount. And we have 2/3 is a batch, so I just wrote that as a B for a batch. And we're trying to figure out how many of these reds, the one I currently have highlighted, will make the entire black. So before I drew this other parts of the red right here, this was just one of those same thing of you have 2 strips, a black and a red strip. How many reds does it take to make black? In other words, how do you scale red to make black? And the way we're going to do that is, well, there's a variety of ways of doing this. You could take the batch, which I have highlighted currently, and shrink it down to 1/2. So here's a half batch. And then do 7 of those to make the 7/3 to get back to that whole length. So if I do 7 halves of a batch, then I will get how many batches we have. In other words, 7 halves is 3.5. 7 halves batches will make this happen. Or you could just sort of do what I've done here. Here's a batch, here's a second batch, here's a third batch. But then we have how much of a batch is required to get the same length as the black. And you have to be careful here. Each of these little hash marks, in one context, they're thirds. In a different context, they're halves, right? This idea that the same length can be represented by 2 different unit fractions depending on what unit you're talking about. Right? So this length here is 1/3 of a cup, because a cup required, I mean, here's a 1 cup right there, but it's half of a batch, because only 2 of them made a batch. Right? So when you get your final, sometimes a student will say the answer is 3, because 3 batches, and 1/3. So they'll say 3 1/3 is the answer, because they're looking at this and thinking that as 1/3, but it's 1/3 of a cup, but not 1/3 of a batch. It's a half of a batch. So the real answer is 3.5 batches. And then, of course, that just comes out naturally when you do the invert multiply algorithm. If you try to figure out how many 2/3 make 7/3, and quotative division answers that, you set up this division, you invert multiply, and you simplify, reduce the fraction to simpler terms, you get 7 halves, and that means 7 halves batches.